4.2 Addition rule and multiplication rule. Addition rule, a tool to find P of A or B, which is the probability that either event A occurs or event B, or they can happen at the same time, both, as the single outcome of a procedure. The word or in the addition rule is associated with the addition of probabilities or union of events. So probability of A or B is the probability in a single trial event A can occur or B or both of it. So to find probability of A or B, add the number of ways event A can occur and the number of ways B can occur, but add in such a way that every outcome is counted only once. Okay, in other words, if there is a common outcomes, you have to take them out. And of course, you divide by the sample space. I want you to pay attention to this formula. And normally, we would say the probability of A union B. The notation for the union looks like a U. Complementary event was discussed. What we need to remember is that the sum is equal to 1 or 100%. Obviously, when you have number 1, you can see that number 2 comes out of it, or number 3. Remember the first one, and everything else just follows. So this is the addition rule. We have a couple more concepts we want to discuss here. One of them is disjoint or mutually exclusive. Events A and B are considered to be disjoint. That means mutually exclusive if they have nothing in common. The notation would be probability of A intersection B is 0. We use a notation that looks almost like an N. And so the thing I want to add here is the following. A intersection B is an empty set. The notation phi means an empty set. I hope everybody remembers that from the basic set theory that we studied in algebra. Now, take a look at the bottom before we move on. We see the Venn diagram. If you look at the left side, they have something in common. This portion, this is in common between the two events A and B. So that would be probability of A and B. By the way, if the Venn diagram is representing the probability, therefore the total area must be 1, because the total probability is 1. So if you look at the right side, on the other hand, if they have nothing in common, that is called disjoint. Nothing in common. And this is exactly why when you look at the addition rule, the commonality should come out, because the common area is considered a part of A as well as B. So if you just add them up without taking it out, you are accounting for it 2 times. Multiplication rule says if we want to find probability of A and B, and by the way, another way of saying this intersection is to write it in this manner. Probability of A and B, or probability of A intersection, which is the probability that event A occurs and event B, both of it. The word and in multiplication rule is associated with the multiplication of probabilities. And we discussed that further later on. Compound event is any event combining 2 or more simple events. We have some definition to work with. Let's look at an example. We want to determine which events are mutually exclusive and which are not when a single die is rolled. Let's start with part A. Part A, getting an odd number and getting an even number. What do you think it is? Are they mutually exclusive?
Exclusive.
Because they have nothing to do with each other. When we look at odd numbers, are 1, 3, or 5. Even numbers, 2, 4, 6. Therefore, they must be mutually exclusive. How about part B? It says giving a 3 and getting an odd number. Getting a 3 and an odd number. Remember, the odd numbers are 1, 3, and 5. So definitely, they are not mutually exclusive. The next one says getting an odd number and getting a number less than 4. So getting a number less than 4. So what are the numbers less than 4? 1, 2, 3. And as you can see, 1 and 3 are odd numbers. Therefore, they cannot be mutually exclusive. Finally, getting a number greater than 4. Okay, so what are those numbers? Greater than 4. 5 and 6. 5 is larger, 6 is larger. And getting a number less than 4, obviously they have nothing in common. Less than 4 would be 1, 2, or 3. And that's why there is nothing in common here.
Assume the probability of randomly selecting someone who has sleepwalked is 0.27. So P sleepwalk is equal to 0.27. If a person is randomly selected, find the probability of getting someone who has not sleepwalked.
We are looking at complementary events, and remember, probability of A plus probability of A bar or A complement is 1. So if you want one of them, just subtract 1 from the other because the sum is 1. So probability that has not sleepwalked equals 1 minus the probability the person has sleepwalked. And it's 1 minus 0.27, which is simply 0.73. So simply put, subtract the probability from 1, and that gives you the answer. I'm following the way it's given, but if I was not given this part and I just had this one, then I would probably define sleepwalking as, let's say, S for the sake of argument. Then I would say probability of S is equal to 0.27, and probability of S not would be 1 minus probability of S, and I would plug in. So I like to define the event by a variable to make life easier as we do the writing.
In a hospital unit, there are 8 nurses and 5 physicians. 7 nurses and 3 physicians are females. If a staff person is selected, find the probability that the subject is a nurse or a male.
It's important to be able to set up the table to make some sense out of this. And let's do that first in order to answer this. This is extremely important that you try this on your own. If you can make up the table, you're practically done. If you cannot come up with the proper table, you will not get to the answer. I can't emphasize this enough. So we got to put up the table, but you got to be able to do this on your own. So first we have the stats, and we have, this is a contingency table, males, females, and nurses, physicians, and we put in the given information. So in a hospital unit, there are 8 nurses. So right in front of the nurses, under the total column, we put 8, and then there are 5 physicians. So that's how it goes, 8 and 5. So you put in as you get those numbers. 7 nurses and 3 physicians are females. So it is the second column that reads females, we're going to put in 7 and 3. Okay, so we put those numbers. If a staff person is selected, find the probability that the subject is a nurse or male. So number 1, we should be able to finish this by doing the following. Look at the very first row. We have nurses. Under females, we have 7. Under total, we have 8. So how many males we have? 8 minus 7, which is 1. Physicians, we have a total of 5. 3 of them are females. So 5 minus 3 must be males. And finally, we have the total. If we add up each column, this is what we get. This is the most important step in handling this question. Now that we have that, we want the probability, find the probability that the subject is a nurse or a male. So probability of nurse or male. We are looking at this union of events. And so the probability of A plus probability of B minus probability of A intersection B, that means the probability of nurse plus the probability of males, that probability of N and M, if you will, minus the probability of those that are in common between the nurses and the males. So when we look at nurses, we have a total of 8, so 8 out of 13. Males, we have a total of 3 out of 13. Now, how many of those males are nurses, or how many of those nurses are males in common? So it's important to see one way to look at it. Look at the lines that I'm going to draw. This one and this one has this one in common. That's the idea. And that's the answer. 8 plus 3 minus 1 over the common denominator of 13 And that's the final answer for this question. Multiplication rule.
The probability of A and B is equal to the probability of event A occurs in the first trial and event B occurs in a second trial. Probability of B
Given A.
represents the probability of event B occurring after it is assumed that event A has already occurred. To find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B, and be sure that the probability of event B is found by assuming that event A has already occurred.
This is the multiplication rule, and it becomes clear as we look at examples. The idea is that the probability of A and B, or the intersection, that I like to use a mathematical symbol. Basically, you multiply the probability of A and probability of B if they are independent. If they are not, then you have to pay attention to this conditional probability of A given B, or in this case, B given A. Okay, that's how it's read. We will discuss that as we go through it, and we look at some examples.
Independent. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. If A and B are not independent, they are said to be dependent.
I want to discuss this concept because you can read this definition a billion times, and it really doesn't make that much of a sense. I'm going to tell you what I mean by that. It says two events are independent if the occurrence of one doesn't affect the occurrence of the other. What does it mean? Well, I'll show you what it means mathematically. When we come across it, I'll show you with numbers, because the definition is, to me at least, it's extremely vague, and one may have a different interpretation than the other. But we use numbers to show that events are independent or not. There are cases that are very straightforward when we discuss them, but if we are dealing with the probability and the numbers are given and we have no idea whether the events are independent or not, then we look at the probabilities and we decide. I'll tell you what we mean by that as we come across it again.
Sampling. In the world of statistics, sampling methods are critically important, and the following relationship hold. Sampling with replacement selections are independent events. Sampling without replacement selections are dependent events.
Just to give you an idea of what's happening here, and again, that one is straightforward. What is not straightforward, the things that we come across and we see, it's really confusing in a moment. But what is straightforward? If you consider the following situation, going back to the example of stat students, we have 40 students. Again, we are just making things up for the sake of argument. There are 40 students. Let's say 21 females, 19 males. We are making things up. So the probability of picking a female, if we pick a student randomly, is 21 over 40. Probability of M randomly, 19 over 40. So I want to explain this concept. It's extremely important. So if we pick a student randomly, what is the probability that students is a female is 21 out of 40 and male is 19 out of 40. Now, if we want to pick another student, well, there are two ways to do that. With replacement. That means the same student that was picked in the first case still has a chance of getting picked. So the probability of females and probability of males stays the same. It never changes. They are independent. However, if you are interested in picking, let's say, two students for a committee, to be a member of a committee, then it's not with replacement. We pick one student. And what is the probability that that student is a female? The very first pick, the first choice would be 21 out of 40. But what happens to the second student? Well, what is the probability that the second student is a female? It really depends. What does it depend on? Depends on what happened in the first place. If we picked a female versus a male in our first choice, then it makes a difference. As far as the denominator is concerned, the denominator goes down to 39. But the numerator, if no female has been picked, the numerator remains as 21. But if one female has been picked, then it goes down to 20. So this is the concept of independency and dependency when it comes to with and without replacement. Finally, probability of A intersection B is probability of A times probability of B in the case of independence. If not, then the probability, and I put actually here and I put the notation here on purpose because I want you to be exposed to both of them, okay? Normally I like to use the notation. Then it would be the probability of A times the probability of B given A. This is read as given. That means A has already occurred. That would be in the case of a dependent. Let's look at an example.
50 test results from the subjects who used drugs are shown below. A. If 2 of these 50 subjects are randomly selected with replacement, find the probability the first selected person has a positive test result and the second selected person has a negative test result.
This is with replacement. The first selection is positive and the second selection is negative. So we really use the basic formula of independency as follows. Probability of A intersection B is the probability of A times the probability of B. So what is the probability that the first selection is positive? Okay, we have 45 that have tested positive, so 45 out of 50. And the second one is negative, 5 tested negative. So 5 out of 50. And we simplify. So 5 and 50, they cancel out to 1 over 10. And then this one gives you 9, this one gives you 10, and that's how you get to 9 over 100. So that's an independent case because it was done with the replacement. However, what happens in RP? We're going to repeat the same thing, but this time without replacement. So when we do without replacement, we have to use the formula at top. Probability of A intersection B is probability of A times the probability of B given that A has occurred. Now, what is the probability of A? The probability of A remains as 45 over 50. That doesn't change. If we choose a person that is selected positive, it's 45 out of 50. That means all the negative ones are intact. All 5 are intact. However, the total, which was 50, goes down to 49. Probability of A is the same as part A. But what is the probability of B now? It's B given A because A has already occurred and it's without replacement, so we got to account for that. Because A has occurred, the total of 50 has gone down to 49. And now you simplify that one. Treating dependent events and independent events with a 5% guideline.
When sampling without replacement and the sample size is no more than 5% of the size of the population, treat the selections as being independent even though they are actually dependent.
Okay, let's see what we mean by that.
Example 5. 3 adults are randomly selected without replacement from the 247,436,830 adults in the U.S. Also assume that 10% of adults in the United States use drugs. Find the probability that the 3 selected adults all use drugs.
So this is actually the explanation of what was that 5% guidelines. And again, that's not a 5% that everybody uses, but just to give you an idea. The fact of the matter is that you're only using 3 adults, which is a lot less than 5%. Although this is without replacement, and therefore you are dealing with a dependent event. They are dependent. I can't emphasize this enough. They are not independent. However, the number that we are using compared to 247 million is so small, definitely less than 5%, then you're going to assume independence. And that's the idea behind that. So with that being the case, the probability that somebody has used it is 10% using drugs. So what we are doing is that we are assuming probability that somebody is using drug and someone else using drug, they are independent. And therefore, each person has a chance of 10%. And if you have 3 of them, then all of them are the same 0.1, we're going to multiply by each other, or 0.1 to the third. So P of all three adults use drugs would be the probability of the first one using drugs, which is 10%. The second one does the same thing, which is 10%, and the last one. In other words, we could write this one as 0.1 to the power of, there are three people. Okay, that's a nice shorthand notation. And so the probability that the three selected adults all use drugs will be about 1 out of 1,000. That's the idea of 5% guideline. When you're dealing with a large population, then sample size, and if you pick then three, then if you picked 10,000 people, again, that would be considered independent because it's a lot less than 5% when you calculate it. With that being the case, let's look at this one, redundancy.
Redundancy, important application of the multiplication rule. The principle of redundancy is used to increase the reliability of many systems. Our eyes have passive redundancy in the sense that if one of them fails, we continue to see. An important finding of modern biology is that genes in an organism can often work in place of each other. Engineers often design redundant components so that the whole system will not fail because of the failure of a single component. Modern aircraft are now highly reliable, and one factor contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems to move and activate landing gear, flaps, and brakes. So if any one system fails, full flight control is maintained with another functioning system.
For a typical flight, the probability of an aircraft's engine hydraulic system failure is 0.002%. If the aircraft had only one hydraulic system, what is the probability that the aircraft's flight control would work for a flight?
This is the complementary event. It has a chance of 0.002 to fail. So 1 minus that would be the complementary event. And the chance of not failing is 99.8% or 0.998.
An aircraft has 3 independent hydraulic systems. What is the probability that on a typical flight, control can be maintained with a working hydraulic system?
They are independent. And so because they are independent, even if one of them works, they will work. So the only way that it fails, if all of them fail. If the system is independent, it can really save lives. And so all of them can fail with the following probability, 0.002 to the third power. Okay. One easy notation would be 0.002 to the power of however many are independent systems to the third. So this is the probability of failing, and therefore complementary event is answer 1 minus this, and as you can see, the probability is almost 0. All right, let's look at the last page.
A simulation of a procedure is a process that behaves the same way as a procedure so that similar results are produced. In many experiments, random numbers are used in the simulation naturally occurring events. Below are some ways to generate random numbers.
Simulation, sometimes we can't actually do the experiment. Simulation will do the job. Here's gender selection.
Gender selection. When testing techniques of gender selection, medical researchers need to know probability values of different outcomes, such as the probability of getting at least 60 girls among 100 children. Assuming that male and female births are equally likely, describe a simulation that results in genders of 100 newborn babies.
So we want to see if there's any simulation that does that. And of course, basically, you look at the concept of 2 outcomes that are equally likely. And that's the idea behind that. So with that case, this would be solution 1. Fair cone means probability of heads and tails are the same, 50%, 1/2. And then you look at that and see what you get. For example, first you have to decide which one represents which. Heads, for example, female, tails, males, or vice versa. It makes no difference. Make a decision and go. Decision has to be made before we start. Then would be going with zeros and ones. A zero represents one gender, one represents another one. Again, make a decision and then go. Okay, for example, zero represents male and one represents female. So you want to change this to female.